Hello, we are Team Clean Hydrogen Power Generation, and this is our project video. Without further ado, let's get into our project's introduction.
Our project is focused on designing a large-scale paper design of a hydrogen production and power generation plant to provide efficient energy solutions for off-site operations that require significant amounts of power, such as mining. To better understand this process, we're building a prototype that generates hydrogen using solar power, stores it, and converts it back into electricity when needed. The insights and challenges we encounter during this phase will guide us in the development of our large-scale paper design. Clean hydrogen plays a key role in addressing a major challenge in renewable energy, and that is finding efficient ways to store energy. Since sources like solar and wind are intermittent, we need a way to store energy for later use. Hydrogen is a promising solution because, unlike batteries, it can be stored indefinitely and in large quantities without degrading or causing environmental harm. Plus, when it's used in a fuel cell, its only byproduct is water, making it a clean and sustainable option for energy storage.
In this project, we set out to harness solar energy to generate clean hydrogen fuel. At the heart of it all is a simple, powerful goal: turning sunlight into storable, usable energy through water electrolysis. We start with two 450-watt solar panels, which capture solar energy and convert it into direct current electricity. The current flows through a fuse for circuit protection and then into a charge controller. From the charge controller, electricity flows into our control gates. From the control gates, it goes into our buck converter. The converter allows the electrolyzers to run at up to 14 amps, the range where it is most efficient. Now comes the core of the system, the PEM electrolyzer. This device uses electricity to split water into hydrogen and oxygen through a process called electrolysis, the only byproduct being hydrogen gas, oxygen gas, and heat. We chose the PEM electrolyzer for several reasons. It is compact, responsive, and ideal for solar-powered applications.
Our system utilizes a water displacement method to safely store hydrogen gas at low pressure. The core of the design is a 2-gallon inverted bucket, which acts as the gas storage vessel and is fully submerged in a large water-filled container. Prior to hydrogen introduction, all trapped air is purged from the bucket, creating a vacuum-like environment. Hydrogen is then pumped into the bucket from the bottom, displacing the water and filling the space with low-pressure gas. When energy is required, a solenoid valve connected to the fuel cell opens, and a diaphragm pump begins drawing hydrogen from the storage bucket. The gas is then routed through a filter dryer to remove residual moisture and a flow regulator to ensure stable and controlled delivery. Finally, the hydrogen reaches the fuel cell, where it is converted into electricity. This method offers a simple and safe approach to storing hydrogen for small-scale renewable energy applications.
In this section, we are looking at the sensor implementation in our system. Here, we have our hydrogen sensor. It continuously measures the hydrogen concentration in our system. If a leak is detected, the control software immediately triggers a system shutdown to prevent risks. Next, we have our temperature sensor, which tracks the electrolyzer's temperature. If the temperature rises above our predefined limit, the system automatically shuts off to protect the electrolyzer from overheating. Our water level sensor keeps track of the electrolyzer's reservoir. Should the water level fall below the minimum operational threshold, the system issues an alert on the display panel. This ensures you never run the electrolyzer dry, which could damage the system components. Here, we show our human-machine interface. The display panel presents hydrogen, temperature, and water level data. Users can press the button to cycle or scroll through each sensor's data readings, and for emergencies or maintenance, a manual switch instantly cuts power off the entire system. Finally, we have the Arduino, which serves as the brain of our system. It pulls each sensor's data in real time, evaluates safety thresholds, and executes shutdown on command. Whether triggered by a sensor's fault or the manual switch, it instructs the charge controller to stop power from the solar panel and the battery, ensuring safe and reliable operation.
Our prototype shows that we can use solar energy to create hydrogen that can be stored and later converted back into electricity. Now we are taking that concept to the next level, scaling up the design to support industrial level hydrogen production. This scaled-up design has a few major components. The first of these is a 55 kilowatt solar array that goes through DC to AC converters. That power is used for the electrolysis process as well as any other needs the plant has, such as a control house with system monitoring. At the heart of our scaled system is the PEM electrolyzer, capable of producing up to 6 cubic meters or about 4.3 kilograms of hydrogen every 8 hours. To support that, we included a 100-gallon deionized water tank, which is able to support about a week's worth of hydrogen production. For hydrogen storage, we used 2 Type 4 hydrogen tanks with a combined capacity of over 8 kilograms of hydrogen, which is enough to provide power for up to 28 hours using our fuel cells. These fuel cells can each output up to 5 kilowatts of power. This design also includes hydrogen pumps that can be used to fill hydrogen-powered vehicles.
A very important aspect of our design is efficiency. In scaling up, we encounter new efficiency challenges. Unlike our prototype, which had 70 to 80% electrolyzer efficiency, the industrial electrolyzer includes internal components that consume additional energy, lowering the system-wide efficiency to about 44%. However, this is still a competitive value. For context, similar systems consume more energy per cubic meter of hydrogen. Our chosen model sits at 6.8 kilowatt hours per cubic meter, better than some other commercially available units. Further improvements of efficiency can be made when increasing the size of these systems, but in order to stay within our scope, we met at a middle ground. We also added safety features like leak detection, filter dryers for moisture removal, and automatic shutoff mechanisms. These improvements ensure that our system is not only functional, but compliant with ISO, NFPA, and IEEE standards. What can we do with this research? This scale design is built for real-world deployment, whether for off-grid backup power, renewable energy storage, or long-duration energy supply in remote environments. With modularity in mind, the system can be adapted to meet larger demands simply by replicating its components. Further steps in this research project would involve performance testing, optimization for even higher efficiency, and exploring deployment in partnership with stakeholders. Ultimately, our goal is to make clean hydrogen not just feasible, but practical for daily energy needs.